let's fill up this bowl with this green water. We can graph the height of the water. So on the x-axis, I've plotted time in seconds, and on the y-axis, I've plotted the water's height in pixels. And here's the curve that I get. Each of these little crosses is one of the measurements that I made at some given time. I measured the height of the water, and I get this curve. What do you notice about this graph? So one thing I notice right off the bat is that the water level increases fairly rapidly at first, but at the end of this process, the water level is still increasing, but it's increasing more slowly. Of course, this makes sense since this bowl is narrower at the bottom than it is at the top, and the water is coming in at a constant rate. A bit more formally, right, dV dt, the change in volume of water over time, that's constant. I'm pouring in water at a constant rate. But dH dt starts off very large. The water's height is increasing very rapidly at first, and by the end of this process, dH dt is small. So I'd like a function that relates water height to volume. Well, if I take a look at the side of the bowl starts off fairly slanted and then sort of flattens out. And that's what I'm graphing here. I'm graphing the radius of the bowl. On the x-axis, I'm plotting the height. That's how far I am from the bottom of the bowl. And as I move up the bowl, the radius of the bowl is increasing, and that's what I'm plotting on the y-axis. And if you look at the bowl, right, the bottom of the bowl starts off very slanted, and then it sort of flattens out. And that's exactly what I'm representing here with this broken line. Right? The bowl starts off fairly slanted and then flattens out. Once I know what the radius of the bowl is at a particular height, I can then think about the volume of water when the water level is at some given height. So once I know the radius of the bowl at a particular height from the bottom of the bowl, I can then make a graph that shows the volume of water in the bowl given a particular height of water. So here on the x-axis, I'm plotting the height of the water, and on the y-axis, I'm plotting the volume of water in the bowl. And you can see that when the water is deeper, there's more water in the bowl, right? I mean, this is an increasing function. Now let's think a little bit about the slope of the tangent line to this graph. So the tangent line initially has a not very large slope compared to after a while the tangent line has a much higher slope. And what that really means is that initially for a given change in volume there's quite a change in the height of the water, but after a while the same change in volume leads to a less dramatic change in the height of the water. That really makes sense from our original experience when we poured all that water into the bowl. When we think back to a graph of the water level in the bowl, here I've got time, here I've got the height of the water is flowing in at a constant change in volume per unit time, and initially, right, this slope of this tangent line is quite high because the water height is increasing very rapidly, but after a while, because there's the same change in volume during this entire process, the change in the water height is less dramatic, right? It's the same amount of water coming in, but the water is moving up the sides of the bowl less quickly.